Hi there. So the first thing I have to say is I'm actually presenting a work that is not my own work, but the work of Vincent Janson. We really would have loved to send Vincent, but unfortunately, logistically, it was not possible to have him here. So I'm presenting on his behalf. And these are excerpts from his master thesis. Now, with regard to the topic of the work, we started looking at SCL4. At the same time, we are also always concerned with safety. I'm from the Institute of Flight Systems at the German Aerospace Center, so safety plays some role. And we are interested in ways that we can support modern use cases in the aviation space. Some of which maybe require the reconfiguration of hardware with partitioning in there and with acceleration in there for something AI. And basically we tasked Vincent with finding a solution to this and set him off for his thesis, and this is what he found. With a rough idea on the schedule here, we are going to start with a little motivation. So what is the use case really that we are looking at? And then we'll go into some of the background that is needed to understand this. There will be some things that you most likely already know, but still we have it in there. Then I'll present the approach that Vincent came up with tinkering and solving these problems, and there's also a little demonstration in the end. So the overall topic that we have is mostly concerned about what is commonly referred to as a transport revolution. So more autonomy in different kinds of vehicles. Now we are an aviation-focused group, so we were mostly looking at eVTOLs, so electrical vertical takeoff. When we set out with this thesis, we had two companies that were doing that in Germany, Volocopter and Lilium. They both went bankrupt by now. I promise this is not due to us, but well. So the overall scope here is we have many small individual aircrafts which can be piloted by non-professionals, and so we need a high degree of autonomy. When we think a bit more about the requirements that this kind of use case brings with it, basically we have three things that we want to tackle at the same time. The first thing is these platforms are small, and so we cannot put a data center into them. So our computing environment probably is going to be something embedded, something with a power constraint, with a heat constraint, so we have to be careful how much resources we require. The second thing, most autonomy features incorporate some kind of machine learning or AI, so there's still some number crunching to be done. We want to do this efficiently, and in the best case, the deployment of AI applications should be simple. So it is probably not feasible to expect of those developing the AI platforms to build a DSP or an ASIC specifically for that application. So it needs to be somewhat manageable. Last but not least, if safety is involved, we do have to think a bit about certification. So there's certain things which are easier to certify and certain things which are not certifiable as far as current status quo goes. So we want to stick to solutions and design principles which are somewhat compatible with how certification is done in the aviation space today. So with these requirements set out, we went into the supermarket and did some ingredients shopping, and it became quite evident to us that heterogeneous system-on-a-chip solutions are quite attractive. What do I mean by this? These are custom silicon that you can buy from certain vendors that incorporates a various mixture of different components, such as multi-core CPU that can run traditional software tasks, but also a Field Programmable Gate Array, so an FPGA that allows us to have custom circuitry built that is in particular very deterministic with regard to timing. Basically down to the clock we control how the circuitry works. Now the question is, given the aforementioned requirements, how can we combine this together? The classical approach for this, in general, if you have an application or multiple applications you want to put into something that is safety critical, is you take some kind of hypervisor or partitioning real-time operating system. By partitioning I mean we have different isolation domains which enjoy some kind of temporal and spatial isolations against each other. And we use that. We have the partitioning as defined in some standards, then we have some kind of API for this. In the aviation case, the predominant one would be ARINC 653. And we integrate that. Now, to this classical approach that is already there and has been practiced for 20 plus years, we want to combine the programmable hardware, the FPGA, in such a way that the hypervisor concept is kind of extended in that we also have the FPGA. what do I mean by kind of extended? So for most realistic use cases, we have more than one application, and that's why we have a hypervisor or partitioning operating system, so that we can host multiple applications on the same compute platform. We want to achieve the same with the FPGA. In the best case, in a way that the different teams that are working on the different applications which are accelerated through some circuitry on the FPGA don't need to talk too much to each other. So here is the example architecture, like the rough idea that we came up with, and we have a couple of different applications here. We have, for example, the attitude control that maybe uses some information that is gathered using a beamforming radar, so it can scan the soil below and avoid a controlled flight into terrain. And at the same time, we maybe have some traffic detection that does some kind of computer vision to detect using an optical system or the aircraft to avoid crashes in the air. And we want this to be integrated. So that's it with the motivation. Now we have to go through some definitions. The first one, I hope this one is no surprise to no one. SAL4 is a microkernel, and you can use it as a hypervisor. A particular set of properties of SAL4 are interesting for us in this use case. The first one is that SAL4 is kind of small with regard to the code closure. There's not so many lines of code going in it. That's really nice if you want to eventually certify it, which hopefully will still be done this decade. Then there is the wide platform support. So in particular, these small embedded platforms usually come with ARM processors nowadays, especially the SoCs that also bring an FPGA. So having ARM support is really nice. Performance is good. There's also this formally verification stuff that we've just heard about. And in particular, SAL4 is already kind of moved past the purely academic exercise status. So there's some real-world adoption of SAL4 that is growing. So seems to be kind of a good bet. The next important bit that we are going to use in this is Microkit. We've already heard about it in the keynote. If you have not gotten the memo on Microkit, I highly recommend you take a look at it. There's a really nice tutorial that's quite fun and not too long to play through. So what is Microkit? In the end, that's a software development kit which solves the biggest problem that SAL4 has, which is its complexity to quite a satisfiable amount. In that, with Microkit, it's relatively easy to develop an application. In the end, it's running on SAL4. Microkit is a very thin abstraction layer on top of SAL4. But you don't need to think too much about radix trees and capabilities. You can just start hacking, really. In Microkit, there is a couple of terms that I want to define here. So there's the term of the protection domain. I'll be using this one equivalent with the term of the partition. We've had the same already happening in the keynote. And then there's also the allocation of resources to these protection domains as per a system definition file. So that is, for example, memory regions, how we map interrupts into notifications inside of the protection domains, but also the configuration of the communication channels between these individual protection domains. So the next point, in the title we had something about reconfiguration, and that is one ambition that we have. We want to be able to reconfigure not only in the software but also in the hardware what kind of accelerators we're running. A reason for this could be that we have, for example, two different sets of AI applications for computer vision. Think about the collision avoidance in the air, and so quite likely we cannot fit all accelerator cores that will be needed at some times in the system at the same time into the FPGA, because it only has a limited amount of gates. And thus we want to be able to reconfigure the FPGA. Now, how does the FPGA generally work? So the pattern that seems to be eminent in current designs is that we have an array of logic cells, and these logic cells are connected via interconnects. And you can basically program any kind of logic function inside of these logic cells, but you are constrained with the number of inputs and outputs. This configuration works by having an SRAM that is on top of the FPGA, and the SRAM basically just toggles on or off independent hardware circuitry, and thus we can, within the constraints of the amount of hardware circuitry that is in the lower layer here, configure kind of arbitrary functions into the FPGA. Important to notice here, at boot up, I can load a different configuration into this SRAM, and thus my FPGA will behave as a different electrical circuit. And I can, even at runtime with modern FPGAs, change parts of this SRAM configuration as to change what kind of electrical circuit the FPGA is hosting during runtime. Okay, with operating systems and programmable hardware a bit of the way, we can now take a look at the rather boring part of the domain, which is standards and certification. So in general, when we have an avionics system, there is always the question of safety and the question of assurance. We want to be assured that the system has the intended behavior, and in the best case, only the intended behavior. So the assurance basically requires you to do all different kinds of work, like writing tests and verifying that the tests reach a certain coverage criteria on the code, and the level of rigor that you're required to do this with is defined in assurance levels. Now, in the aviation industry, we have the assurance levels in the table on the right, with A being the most critical one, so there's the most work when you do the verification, because we are assuming that if the system fails, there will be catastrophic events following, while on level E, there's basically almost no verification required, because the system does not contribute to the overall safety of an aircraft. Obviously, higher assurance level requires more evidence. Now, if we take a look at the landscape of these things, I'll try to use the laser pointer emulator here. We have different layers on standards that combine these things. If we work from the top, there's the ARP 4761, which generally concerns with the safety assurance and the process for making sure the aircraft stays in the air. Below that, we have the ARP 475A, 54A, which concerns with the integration of different parts, different subsets of an aircraft, so the system level. And then on the actual implementation level at the bottom here, on the left-hand side, we have the programmable logic, which is guarded by DO254. That's the standard for hardware and electronics in particular. So if you have an implementation of a particular equipment or device, you want to look into that standard. On the right-hand side, we have the DO178C. That's kind of the Bible of software development for aircrafts. And that would be, for example, where we have to look with regard to verifying SAL4. So that was a lot of definitions and background. So the next thing we are going to look into is the actual approach that was found by Vincent. So in particular, we already, with the ingredients shopping, committed to using a heterogeneous SoC that combines an FPGA and a CPU. And the critical parts that we identified here are, for most, we want to be able to virtualize the FPGA, in particular accelerator cores running on the FPGA, from the perspective of the software. So this is the first point on the left side. I still have the laser pointer, so this is here. The second point that needs to be working well is we want to actually run the accelerators on the hardware. So we need to implement them in the FPGA. And we also need some kind of management for these. Most of the time, I assume if we have an accelerator, we are probably going with a job-oriented model. I can submit a job. It gets processed by the accelerator, and then it yields a result in the end. The second point that we also want to achieve is reconfiguration. So we want to change the accelerator cores at runtime. Now we have these two domains, the PL and the PS, the programmable software and the programmable logic. And these need to communicate. So the third critical aspect of this implementation and this ambition is that we need to get the interaction between the CPU and the FPGA to work just right. So in particular, how can we do this cross-domain communication? The starting point here is that we actually have the possibility of shared memory between them. So like most modern devices, shared memory will be like the vehicle that we use to transmit data. And the design that we came up with, seeming to be the most suitable, is that we have on the one end a DMA engine, and the DMA engine can transfer data from the main memory that is accessible to the processor into block RAM from the FPGA and backwards. And we also have a set of memory mapped registers using an AXI register interface that allows us to have small amount of data that is directly accessible both to the programmable logic and to the programmable software. Now, these both things, the AXI interface and the DMA, are integrated on the FPGA, while the SEL4 kernel is our baseline for the software side. There's a couple of design decisions when implementing this that came up. Most notably, these two were things where we did some investigation before we settled on something. The first one was, how do we actually do the access of the protection domains to the hardware accelerators? Thinking in terms of Microkit, what we could do is that we have a memory region which is directly accessible to one accelerator core and to a protection domain, and via this and maybe some interrupt delegation, we can have a direct communication going on. In the end, this is maybe not the best idea, because it makes sense to filter to some degree what kind of jobs can be submitted to an accelerator core. Then we can also implement some kind of scheduling if there's multiple applications. And in particular, we have a higher degree of isolation between these environments. And therefore, here Vincent opted to go for an indirect access, so to implement a hardware accelerator virtualizer in software. And only this virtualizer running in a separate protection domain actually has access to the control registers for the FPGA. The principle that led this design was basically the principle of least privilege and the principle of resource partitioning. The second question was, how shall this be implemented on the SEL4 side, so in particular the virtualizer? This is a bit of a provocation, I guess, because the answer is quite clear to most people here. You could either extend the SEL4 kernel and build functionality for this right into it, or you could subscribe to the belief that a microkernel is perfectly suited for having this kind of functionality factored out into a separate protection domain. And so that is also the choice that became here. So with the implementation constraints and some of the rough ideas out of the way, this is the building blocks that needed to be integrated for the demonstration and for the implementation of the final concept. Luckily, we found quite a lot of already existing blocks that we could rely on. These are marked green here. And we found also some existing IP that could be customized to fit our use case. This is marked violet in the graph on the top left. In particular, some of the things also had to be implemented by hand. The most important one here is the accelerator management. That's essentially a state machine that's running on the FPGA, which is managing the different accelerator cores. One thing of note here, as we set out with this claim that basically we want a hypervisor, but also we want the hypervisor to manage the hardware accelerator cores, is this kind of equivalence that we have on the bottom line here, where we have 3 different layers. In software, we know these layers. We have an application that's supervised maybe by an operating system, and then a hypervisor that's supervising multiple of these virtual machines or protection domains. And on the right-hand side, we have a similar mapping to the FPGA. In this case, on the lowest level, you have the individual accelerator cores. In the supervisor level, we manage the accelerator management, of which there can be multiple, each one taking care of an individual set of accelerator cores. And then on the top level, we would have the reconfiguration management, which basically moderates access to the FPGA as a limited resource in a similar way that the hypervisor moderates access to a processing unit's resources. With all that out of the way, let's jump to the final system architecture that was envisioned for this. So, in essence, we have a set of protection domains. These are the actual applications, denoted PD1, PD2, PD3, etc. And they are all running on top of SEL4, of course. These can, via protected procedure calls, call into the accelerator handler, which is another software component running on SEL4, which, however, has the privilege of accessing the control registers to the FPGA. Via these control registers, the handler can forward, in essence, a job to one of the accelerator cores, which is received via a protected procedure call, into the FPGA. Via the AXI Lite, we can then receive this information, or basically read the change of the configuration registers, and in turn have the accelerator management, which internally has a state machine for the job scheduling of individual jobs, take care of a job. Mostly what this means is, if the current configuration is fine, we don't need to reconfigure, if there's a problem with the current configuration, if we need a different accelerator core than the ones which are currently loaded, then we can reconfigure. Once we have all the accelerators that we need for the current job in place, the accelerator then is actually started. So we start via the DMA transfer, a load of the actual job data from main memory into the block RAM of the FPGA. The accelerator does its magic, does some number crunching, and returns the result, again via a DMA transfer to the main memory of the processing system. Finally, an interrupt is used to communicate to the processing system that the job is done, which in turn triggers a notification in the handler, which in turn, via a notification, signals the availability of data to the protection domain, which at the start actually requested the acceleration job. Now, there's quite a lot of things that need to be properly integrated for this, and we were keen to find out if that works. We did come up with a demonstrator which implements some of the things which are demonstrated, which are shown in the envisioned architecture. In particular, this is a demonstrator architecture which we have. There's a couple of limitations where, due to time constraints in this master thesis, we limited ourselves to a subset of the final features that such a system should be having. So in particular, we have two protection domains here, and we opted for skipping actual implementing the hardware acceleration. Instead, the hardware acceleration is just a mock-up, which counts a counter upwards. So there's some delay in the hardware that is quite predictable, but it doesn't do any actual number crunching that goes beyond add one. The next limitation that we went on is that the protection domains which are to submit the jobs are dummy protection domains, so they do submit a job, but there's no actual radar-based beamforming, altitude hold, or any other functionality built into them. And the last limitation that we went on is we constrained the DMA transfers to be 64 bytes. That was a default size, which worked well. In a real system, obviously, you want to support jobs which are larger than that. Now, with these constraints, Vincent actually implemented the demonstrator and got things to work mostly. In particular, the system behavior works. We can go with a round trip with an accelerator job that goes from a protection domain through the handler, through the FPGA, again back to the protection domain that requested that job. However, there were a couple of problems with our results. In particular, on the non-functional behavior side, there were quite some delays for the propagation of data, which is written to the control registers via the AXI light interface. So it took more time for the FPGA to notice that something is needed to be done than we hoped for. At the same time, we also ran into some issues with a backwards propagation, so the interrupt signal, which needs to be created by the FPGA and then sensed by SCL4, took longer than we anticipated to be noticed, and longer than it actually says in the TRM. Could be that we have an error in our PL implementation with regard to that signal, but we weren't able to figure out what the error is, and so now it takes, I think, roughly 5 times more clock cycles than actually described in the TRM. And last but not least, the DMA core that we used performed much worse than we expected it to be. I think we can take a rough look into the timing here. This is the timing of different signals of the FPGA. It's gathered using an external device. And so it's probably fine with regard to the resolution of time. We can see here in particular that the timing from the DMA read enable, so once the DMA controller is free to read data from the main memory of the processing system into the block RAM of the FPGA, took about 550 nanoseconds or so. And for the amount of data that we have, that roughs out to somewhere around 120 megabytes per second, but given the width of the DMA engine, we would expect it more to be in the vicinity of 380 megabytes. Other than that, we can see that there's a quite reliable 500 nanoseconds delay of the hardware accelerator dummy. That's just a counter that at 100 hertz counts from 0 to 50. And we can see that write back from the block RAM to the main memory of the PS side, again, is in the vicinity of 500 nanoseconds. So again, around 120 megabytes per second. So the DMA really is not performing as well as we would want. The overall time that we see the data in motion here, only in the FPGA, there's additional delays in the programmable software side, is in the vicinity of, I don't know, maybe 1.6 microseconds or so. That's, I think, what it says in the slide. And so this system is kind of low latency, I would argue, though we are still not satisfied with the exact throughput we can get. So there's a couple of lessons learned that we gathered for this demonstrator. In particular, was one time when we did the first measurements, and this round trip, which now we've seen in the vicinity of somewhere around 2 microseconds with software, maybe 3 or 4 microseconds, it took 20 milliseconds. And we did some tinkering here and there. We tried to debug the problem until when we find out that we had a debug print somewhere that went over a synchronous interface, which was clocked at 115 kilobaud. So that was very, very, very slow. And once we removed the debug print, the problem really was gone, and performance was better, a factor of 12,000 or something. Other than that, it took a significant amount of time to implement the PLPS communication. It's quite tricky to get this working, and I would argue that still, while we can transfer data, we are still not satisfied with the performance there, so that's a tricky one. Microsoft turned out, not Microsoft, Microkit turned out, I'm sorry, there's no recovery from this one. So Microkit turned out to be an excellent choice for this kind of tinkering and implementation. Vincent did not have a lot of experience with microkernels beforehand, and basically it took about a week, and then the first system was running on hardware. And there really were no big roadblocks. There was always a lot of small things and learnings, like the thing with the synchronous printing via UART, but mostly Microkit really worked to our advantage. So this is really a shout out, quite happy with that one. In total, the PS side of this also is quite small in code, about 1,000 lines of C. So this was really, really working well. Last but not least, whoever wants to attempt something like this, buy a good logic analyzer. You will need it. The to-dos that are still remaining here is, in particular, the paper, the proper benchmarking. I tried to remove some of the benchmarking claims we had before I get a conviction by the benchmarking police. But so we definitely want to improve upon performance, and we want to implement the partial bitstream reconfiguration of the FPGA as well. That brings us to the conclusion for this talk. I think the main takeaways here are this hypervisor principle of moderating a couple of resources to multiple applications that want to use them is applicable to hardware and programmable logic. And the microkernel approach in particular works well with this use case. And we did not see any problems with regard to performance or interfacing there. Programmable logic, programmable software interfaces are tricky. That's it from the talk. Thank you.
We're a little short on time for questions. I'll take one, or maybe Dave comes up to...
I'll grab the mic to prevent repeating. So, very quick comment. You misattributed the microkernel minimality principle that's 30 years old and goes back to Jochen Liedtke. The overall approach is totally sensible. An FPGA is just a device and should be treated as that. And we should think about extending that into a proper SDDF device class. My real question is, what does that do to certifiability, in particular real-time performance, if you have the FPGA massively doing memory traffic?
That's an excellent question. The answer is you need to make sure that you know when these transfers are happening, and you have to provide empirical data to show that the transfers are not hurting the real-time performance of your application in an unacceptable way. The state of multi-core interference in certification, to which I would claim this to be a sub-problem, however, is kind of dire. And there have been maybe 2 to 3 certification programs going on since the late 2020s, the early 2020s, that actually succeeded in this. So this is a question that is not definitively answered, and we are unhappy with the answers we have so far.
Cool. Let's thank Wanja.